Okay, this is section 6.5, circular functions, graphs, and properties. Of course, you can graph everything with your graphing calculator, but it's still worth learning them, I guess. Okay, the circular functions, circular as in a circle. Back in section 6.4, we looked at the problem of finding the coordinates of P of t, where t was an arc length measured from the point 1, 0 on the unit circle. We said that was a very tough problem, and it is. So in this section, we give the solution to the problem of finding the coordinates of P of t. A lot of times in mathematics, if we had a difficult problem to make it simple, we just make a definition. So it is done with the following. Let t be a real number, and let P of t with coordinates x, y be the point on the unit circle where an arc of length t that begins at the point A with coordinates 1, 0 ends. Then we have the following circular trigonometric functions. Number 1, the sine of t is y. Number 2, the cosine of t is x. Number 3, the tangent of t is y over x. Number 4, the cosecant of t is 1 over y. Number 5, the secant of t is 1 over x. And then lastly, number 6, the cotangent of t is x over y. If you look at these very closely, hopefully you see a certain relationship. And also, 4 of them have denominators, so 4 of them could possibly be undefined. So these 6 functions are sometimes called, number 1, the circular functions, because they are coming from the unit circle. Or the trig functions, and you'll sometimes hear the circular trig functions. Some important observations. Okay, again, observations about this. Okay, observe, 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 observe. The 3 functions on the right are the circles of the 3 functions on the left, and vice versa. Just like when we defined them earlier. The tangent of t is the sine of t over the cosine of t. Remember, the tangent was y over x. The sine of t was y, the cosine of t was x. The cotangent of t is the cosine of t over the sine of t. Notice, it's still a reciprocal. Flip that guy over. And number 4, since unit circle has the equation x squared plus y squared equals 1, and the cosine of t is x, and the sine of t is equal to y, we have the following Pythagorean identity. The cosine of t squared plus the sine of t squared is equal to 1. T is a real number. That means that we're evaluating the trig functions at real numbers. In other words, radians. So be sure your calculator gets set to radians if you're doing a radian measure. Notation for raising functions to powers. Again, it comes from this observation, cosine of t squared. Because when we say cosine of t squared, how do we know if we're squaring the cosine of t or we're squaring the t? So let n be any number other than -1. And we write the following. For f of x, taken to the nth power, we write f to the nth of x. And that's how we say it, f to the nth of x. So this means first find f of x and then take the result to the nth power. If trig represents any trig function, then if we want the result of evaluating the trig function taken to the nth power, we write this, trig to the nth of x. So this means to first find the trig of x and then take that result to the nth power. To take any function to the -1 power, we write it this way, f of x in parentheses to the -1. Or for the trig function, we write trig of x in parentheses raised to the -1. So warning, never write f to the -1 of x for f to the -1 power. This notation means inverse function. The inverse function is not the reciprocal. Using the correct notation, the Pythagorean identity is written as this. Cosine squared of x plus sine squared of x is equal to 1. And that's how we say it. Cosine squared of x plus sine squared of x is equal to 1. Evaluate the following. Round or final answer 4 places right at the decimal point. Sine cubed of 56 degrees. We're going to have sine, 56, second angle, 1 to make sure we're degrees, close your parenthesis, raise to the 3rd power and enter. About 0.5698. Okay, again, just so you can witness it. Open your parenthesis. I didn't open it here. It didn't cause any confusion, but just to show you it doesn't matter. Sine, 56. And I don't know if I'm in degree mode or not, so second angle, the degrees, symbol, close. That closed that opening one there, and that closed the one that I opened. Raised to the 3rd power. And we get 2 4 places, 0.5698. Cosine of 3.4 cubed. Notice there's no degree symbol, so this is radians. So, to save myself some trouble, since I can make an angle, let me change my mode to radians. So I'm going to have cosine 3.4 raised to the third power, get out of the exponent, close the parentheses, negative 0.0341. Again, you could set your float to 4 to the cosecant to the 4th power of 7.8 degrees. So let's see. I'm going to have 1 divided by, I'm going to open my parentheses, sine 7.8 second angle degree symbol, close the one calculator open, close the one I open, raised to the 4th power, Q947.6863. Now again, be sure you can use your calculator correctly. It's a shame to get calculator problems wrong. Cotangent squared of negative 3.6. So let's see. I do 1 divided by, open parentheses, tangent, negative 3.6, close what, calculator open, close what I open, raised to 2nd power, if you want to hit the x squared for each choice. So 4.1066. We can also use symmetries of the unit circle to find points based upon given points. Remember this, the unit circle has all kinds of symmetries. So we call the following. Symmetry with respect to the x-axis changes the sign of the y-coordinate. Symmetry with respect to the y-axis changes the sign of the x-coordinate. Remember, symmetry with respect to one axis changes the algebra sign of the other coordinate. And number 3, symmetry with respect to the origin changes the sign of both coordinates. Given the point P of t is 0.6, 0.8, find the coordinates of the following points. P of negative t, P of t plus pi, and P of t plus 2 pi. So here's P of t with coordinates 0.6, 0.8. So first question wanted us to find P of negative t. So same distance, but clockwise. So down here, P of negative t. Notice I've gone below the x-axis. The y-coordinate changes sign. So this should be 0.6, negative 0.8. Okay, for number 2, I wanted to do P of t plus pi. So adding pi, I go half a circle. Okay? This point and P of t plus pi are symmetric with respect to the origin. They both change their algebra signs. So it should be negative 0.6, negative 0.8. And again, here's my 0.6, my 0.8. And I wanted to do P of t plus 2 pi. Remember, 2 pi, you go all the way around. So I end up back to where I started. So P of t plus 2 pi is also 0.6, 0.8. It is important for students to know the special values on the unit circle. Again, if you're not one of my students, then you cannot find this in D2L because you don't have a D2L. On the next slide is a sketch of the unit circle with the important points labeled. So notice, here's the degree measure, the radian measure, the coordinates of the point. I'm sure you can find some place on the internet to download this. find the exact values for p of t for each given value of t. So it's kind of like we're going, whoops, let me go back. Let me do what I wanted to do. It's kind of like we're trying to figure out this unit circle thing. So t is pi. I'm looking for p of pi. So it's negative 1, 0 in the unit circle. So then if you go back to that unit circle thing, there's pi, negative 1, 0. Okay. Alternatively, p of t is cosine of t, sine of t, cosine of pi, sine of pi. 5, 5, or 6. Okay, let's do its cosine, sine again. So take out Mr. Calculator. So remember, x is cosine. So cosine 5 pi over 6. And you get that negative 0.866. That's the negative square root 3 over 2, if you want to verify. Negative second square root 3, get that one radical, divided by 2. And the y is the sine. Sine 5 second pi divided by 6. And remember, I have my calculator in radian mode. I get 0.5. So cosine 5 pi over 6, sine 5 pi over 6. Okay. Now then, to do stuff like this, you can just take out your calculator. And in an earlier presentation, we did the square root of 2 over 2, the square root of 3 over 2, and so on like that, your approximations. So, some more examples. Find p of t for each given value of t. Round your final answer to 4 places to the right of that one. So evidently these aren't going to be special. So let me go ahead and set my calculator up correctly. Clear mode. Let's have my float over to, what did it say, 4? Oops. My float over to 4. So remember, the cosine is the x. So cos 5.78, please. And the sine is the y. Sine 5.78, please. So there are my coordinates. 0.8761, negative 0.4822. So cosine t, sine t. Remember, x is cosine, y is sine. T is negative 9. So we'll have cosine of t, sine of t is cosine of negative 9, sine of negative 9. Get negative 0.9111, negative 0.4121. Again, just take out the calculator and play with the buttons. Okay, graphs of the circular functions. Graphs. We're going to look at the graphs and properties of the trig functions. We'll be using the unit circle to help us. That's just going to give us points. So since the points in the unit circle start to repeat after we have made one complete revolution of the unit circle, the values of the trig functions will also start to repeat after a certain point. So the idea of values repeating after a certain point is one of the properties of the 6 trig functions. Remember, all 6 of them do that. So part A here, periodic functions. Definition: a function f is called periodic if there exists a positive number p such that f of x plus p is equal to f of x for all x in the domain of f. The smallest number p for which this is true is also called the period of the function. So the smallest positive number p that makes this true is the period. Notice any multiple of the period will also work. That's why you have to say the smallest positive. Now notice if p is 0, it's kind of stupid. You get f of x is equal to f of x, which, I would hope that's true. As strange as it may sound, there do exist periodic functions that do not have periods. There are a bunch of them. All of the trig functions are periodic, and all of them have periods. We now look at the graphs of the 6 trig functions. In looking at the graphs, we will state the domains, ranges, and periods. Recall that the only problem that we had with the domain was having 0 in the denominator. That will still be the case with the trig function. Remember, the cosine of t was x, the sine of t was y. There's no denominator. So domain and range of sine and cosine don't have issues. The other 4 do. So graphs of the sine function. Domain, range, and period. You recall that on the unit circle, sine of t was y. There's no denominator to worry about. That means the domain is all real numbers. Okay, the sign of t has domain all real numbers. Now, on the unit circle, y ranged from -1 at the bottom at the south pole, +1 at the north pole. So the range of the sine function is -1 to 1. The closed interval -1 to 1. So if you take the sine of something and you get something bigger than 1, like you get 2.7, something went wrong. The sign of t is between plus and -1. On the unit circle, the y values start repeat in the exact same order after one complete revolution. Remember, one complete revolution is 2 pi. So that means the period of the sine function is 2 pi. So the range is going to be all real numbers. The domain is all real numbers. Let's do a summary. Domain, all real numbers, linear rotation, -infinity to infinity. Range, closed interval from -1 to 1. You'll see it sometimes written like this. -1 is less than equal to the sine of t, which is less than equal to 1. And the period, 2 pi. So graphically, if you graph the function from 0 to 2 pi, it'll repeat after that. Just pick it up and move it. So between 2 pi and 4 pi, it looks like it did between 0 and 2 pi. So we just need to graph the sine of the function between 0 and 2 pi, and then use the fact that period is 2 pi to get the rest of the graph. Remember, 0 to 2 pi is something called the basic period. Now, this is where it's going to be confusing. The x-axis, y-axis, please don't confuse them with the x-coordinate on the unit circle and the y-coordinate on the unit circle. So we're really graphing, I guess, we could say y equals sine of x, but it's like f of t equals sine of t. So the portion of the graph from t equals 0 and 2 to 2 pi is called the basic period. So when graphing the trig function, do not confuse x and y for graphing with the x and y values from the unit circle. Remember, we always graph y equals x for any function. Of course, you can take out your calculator. Be sure it's in degree radian mode. So again, let me check mode. Yeah, let me get rid of the float. So you can just, do your y equals. And say that you're plotting sine of x. Where's my x in this thing? Right there. And then just say graph. Now, we usually like to change the scale. Oops. Let's change my window. Let's go from -1.5. And my maximum will be 1.5. Remember, the range is -1 to 1. My x scale, we like to do it in multiples of pi over 2. So second pi divided by 2. Oops. I should have left that at -10 and 10. I was thinking, since I'm doing pi's, let me do 2, oops, -2 pi, the max, let it be 2 pi, and then for my y min, let's let that be -1.5, and my y max, let that be 1.5, and I'll keep my y scale at 1, okay. So put that there, and then let's graph. Now notice, from 0 to 2 pi, that's the basic period. It looks the same as this that went from -2 pi to 0. So when graphing the trig functions, we usually not always mark off the x-axis in multiples of pi over 2. So the graph of y equals sine of x. So the basic period goes from 0 to 2 pi. If we make a table of values, sine of 0 is 0, sine of pi over 2 is 1, sine of pi is 0, sine of 3 pi over 2 is -1. Remember, I just took out my calculator and plotted these. Or if you remember, going around the unit circle, the y coordinate is the sine, and the sine of 2 pi, we're back to 0. So that's what it looks like. That's the basic period. What does it look like from here? Pick this guy up and move it. So hopefully you can see the basic period. It's a little thicker. I'll try to do that on all of them. Okay, from the graph, we have the following properties of y equals sine of x. The x-intercepts are multiples of pi. And if you look at it, the x-intercept, where is it crossing the x-axis? 0, pi, 2 pi, 3 pi, 4 pi, negative pi, negative 2 pi, negative 3 pi, negative 4 pi. The max values or peaks occur when x is at plus or minus pi over 2, plus or minus 5 pi over 2. We usually state it like this: odd multiples of pi over 2. So you have your peaks and valleys at odd multiples of pi over 2. X-intercepts are at multiples of pi. So the minimum values, those are the other odd multiples. Okay. The basic period of the sine curve begins and ends on the x-axis. The midpoint of the basic period of the sine curve corresponds to an x-intercept. The first quarter point of the basic period of the sine curve corresponds to a maximum value, or p. And the third quarter point is a minimum, or valley. So first quarter point is a max, third quarter point is a minimum. Remember, the second quarter point is the midpoint, and that's an x-intercept. Remember, the sine period, the basic period, sine curve, the basic period begins and ends on the x-axis. Okay, the graph is in one piece. That means it's continuous. That's kind of a big deal. The graph of the cosine function. Remember that down the circle, the cosine of 2 is x. No denominator. So domain is all real numbers again. Now, on the unit circle, x went from -1 on the left, kind of the west pole, to +1 on the right, the east pole. So the range is the closed interval from -1 to 1. Okay, and if you're going around the unit circle, x repeats after you've gone through 2 pi radians, so the period is 2 pi. So again, the basic period will be from 0 to 2 pi. So the summary domain, range, and period of the cosine function. Domain, all real numbers, minus infinity to infinity. Range, -1 to 1. Period, 2 pi. So if we take out the calculator and graph it, so let me go to y equal, clear that one out, and let's do cosine. Graph. Okay, from here to here is one basic period, and notice that looks like this side. Now, if you didn't know where I started it, you would say, that looks kind of like the sine function. It does. So the portion of the graph between t equals 0 and t equals 2 pi is called the basic period. And here's the graph. So I'm going to graph it from 0 to 2 pi. So here are my table of values. Again, these are the special arc lengths, the 0, pi over 2 pi, 3 pi over 2, and 2 pi. These values should look vaguely familiar from the sine. You're saying, that looks weird. Yeah. One basic period of the cosine function does look weird. If I complete it, and again, if you didn't know where the y-axis was, you'd say, that looks an awful lot like the sine function. Yes, the sine and cosine function look exactly alike, except one of them is the other one shifted over. And if you don't know where the y-axis is, you couldn't tell them apart. Okay, some observations on this. You notice I have my peaks at 0, 2 pi, 4 pi, negative 2 pi, negative 4 pi, kind of the even multiples of pi. I have my x-intercepts at the odd multiples of pi over 2. I have my valleys at pi, 3 pi, negative 3 pi, the odd multiples of pi. Okay, so x-intercepts, odd multiples of pi over 2. Maximum values are at the even multiples of pi. So when x is an even multiple of pi. Excuse me. Remember, the actual value is 1, the y value. The minimum values occur when the x is equal to an odd multiple of pi. Pi, 3 pi, 4 pi, or 5 pi. Remember, the actual y value, what is the value of the minimum? It's -1. Remember, sine and cosine range between -1 and 1. Okay, the basic period of the cosine curve begins and ends at a maximum value or a peak. Remember, the sine began on the x-axis. The cosine begins up at 0, 1. The midpoint of the basic period of the cosine curve corresponds to a minimum or valley. And the first quarter point and the third quarter point, those are x-intercepts. Notice it's kind of like the sine function with a few minor changes. Sine and cosine look so much alike as to be confusing. Here again, the graph is in one piece, so it's continuous. Again, this is a big deal. It may not sound like it, but it is. Okay, the cosine curve is just the sine curve shifted left by pi over 2 units. Or we could also say that the sine curve is the cosine curve shifted right by pi over 2 units. So for this reason, we sometimes say that sine and cosine are out of phase by pi over 2. Graph of the tangent function. Domain, range, and period. Can you remember, the tangent of t is y over x. I got a denominator to worry about. So we got to worry about, on the unit circle, when is x 0? So we have to exclude the arc lengths where x is 0. Remember, that's going to be up at pi over 2 and negative 3 pi over 2. Then again, at pi over 2, 3 pi over 2, 5 pi over 2, so on like that. So the points are 0, 1, and 0, negative 1. North pole, south pole. So plus or minus pi over 2, plus or minus 3 pi over 2, plus or minus 5 pi over 2. It's the odd multiples of pi over 2. So the domain of the tangent function is all x's such that x is not an odd multiple of pi over 2. Remember, that's where the denominator of this expression is equal to 0. If you recall your days in college algebra, having the denominator equal to 0, that's a vertical asymptote. So the range and period are a little harder to see. It's an interesting exercise and analysis to show that any real number can be written as the ratio of x over y or y over x, whenever x are between x and y are between minus 1 and plus 1. Notice what that means then. The range of the tangent function is all real numbers. Okay. So, the sine and cosine, only one of x or y was used on the unit circle. They gave periods of 2 pi. And remember, tangent uses both of them. So, the period of the tangent is pi. So the tangent has period pi. Okay, so summary of domain, range, and period of the tangent function. Okay, the domain is all x's such that x does not equal an odd multiple of pi over 2. The range is all real numbers, minus infinity to infinity. The period is pi. We will sketch as the basic period minus pi over 2 to positive pi over 2. Okay? And it's an open interval, because remember, the odd multiples of pi over 2 make the denominator equal to 0. Remember, that's where the x-coordinate is 0 on the unit circle. So before graph, I'll actually need to explore what does it mean graphically when the denominator is equal to 0. Since division by 0 is not allowed, the values of x that cause division by 0 force the graph to break apart. The graph breaks apart. It's not in one piece. So vertical asymptotes. A vertical asymptote is a vertical line that a graph gets closer and closer without ever crossing or touching it. As a graph gets closer and closer to a vertical asymptote, the graph will either keep going up higher and higher towards infinity or keep going lower and lower to minus infinity. The graph will never cross a vertical asymptote. Usually we sketch in the asymptotes either very, very lightly or as dotted vertical lines. They kind of act as guides, and they let us know that the pieces of the graph are between those light lines or dotted lines. They're between the vertical asymptotes. So if you have vertical asymptotes, that means your graph either has an incredibly restricted domain or else your graph occurs in a bunch of pieces. So a vertical asymptote, again, make your graph become piecewise. Vertical asymptotes occur where the denominator of a function is equal to 0. Now remember, the tangent of t was y over x. On the unit of circle, x was equal to 0 at the odd multiples of pi over 2. For the six trig functions have vertical asymptotes. The graph will equal tangent of x. Okay, from the domain, we know that we have vertical asymptotes when x is an odd multiple of pi over 2. Okay, we sketch the basic period of the tangent function from the following table of values. Okay, vertical asymptotes at x equals plus or minus pi over 2, plus or minus 3 pi over 2. We draw these as dotted lines. There they are, dotted lines. Our basic period will be in here. And then we'll just pick this guy up and move it to get the other. So we need values between minus pi over 2 and x equals pi over 2. When x is 0, the tangent is 0. When x is pi over 4, the tangent is 1. Again, I just took out my calculator to approximate this. Or if you have that little picture of the unit circle. And at negative pi over 4, the tangent is negative 1. That's enough to draw it. So remember, don't cross the vertical asymptotes. So here's the basic period. Now, depending upon the settings on your calculator, I guess we should turn it back on. So y equal, what y equal, give it to that guy, tangent x, oops, graph. Now clearly my scales are different. And then there's the basic period. To get the rest of them, pick this graph up and move it. Move it, move it. Okay. All of that together is the graph of f of t equals the tangent of t, or y equals tangent of x. Okay, all of it together. Notice it's extremely piecewise. So the graph of the cosecant function. Well, I guess observations like this. The tangent has its x-intercepts at multiples of pi, just like the sine function. And notice it's only y-intercept is the origin. Graph of the cosecant function. Okay, so domain, range, period, and asymptotes. Okay, the graph, on the unit circle, the cosecant of t is 1 over y. Aha, problems with y. So on the unit circle, where is y equal to 0? So the fact that we have a denominator says we've got domain issues, we've got vertical asymptote issues. See, on the unit circle, the y coordinate is 0 at 1, 0, and negative 1, 0. Oh, that's 0, that's pi. Notice 0 is a multiple of pi. So it would be 0, pi, 2 pi, 3 pi, 4 pi, multiples of pi. So the cosecant of t is undefined when t is a multiple of pi. That means I have vertical asymptotes at y equals a multiple of pi. So the graph is in pieces. So domain, set of all x's such that x is not equal to a multiple of pi. Now what about the range? Okay, 1 over y. Remember, y is between negative 1 and 1. So I'm looking at 1 over fractions. These stay away from 1 and stay away from negative 1. So the range is going to be greater than or equal to 1 or less than or equal to minus 1. We sometimes write it like this. Minus infinity to minus 1, union 1 to infinity. Notice it does include minus 1, it does include 1. So divide 1 over y, start repeat in the exact same order after one complete revolution. That's 2 pi. Remember, it only uses 1 over y. It only uses one of the variables. So period 2 pi. Remember, tangent used both x and y at a period pi. So the period is 2 pi. So the sum of domain, range, period, and vertical asymptotes of the cosecant function. Domain, set of all x's such that x is not equal to multiple pi. Range, minus infinity to minus 1, and 1 to infinity. Graphically, that says there's going to be kind of a band between minus 1 and 1 where the graph doesn't occur. Period, 2 pi. Vertical asymptote, x equals a multiple of pi. The graph. So again, we're going to draw it in the basic period. So we usually draw the sine curve and the cosecant. Why the sine curve? Remember, cosecant is a circle of sine. So the cosecant goes like this and then down here. So I've drawn that in lightly. There are my vertical asymptotes. There's the basic period. These two pieces together is the basic period. And then to fill it in, there. All of those heavier red pieces together is the entire graph of y equals the cosecant of x. Notice extremely piecewise. And remember, the secant is going to have the same issue, and the cotangent is going to have the same issue. Graph of the secant function. Okay, domain, range, period, and asymptotes. Okay, remember, on the unit circle, the secant of t was 1 over x. So from the tangent, we know that x is equal to 0 at the odd multiples of pi on the unit circle. So my vertical asymptotes will be y equals an odd, x equals an odd multiple of pi over 2. Notice it's just like the tangent, which should make you believe kind of a foreshadowing that cotangent is probably going to behave that in terms of vertical asymptotes and domain issues, kind of like the cosecant. So we have vertical asymptotes at x equals an odd multiple of pi over 2. Again, my graph is in pieces. So the domain, instead of all x's, such that x is not a multiple of pi over 2, you could say an odd multiple. And since minus 1 to 1, x is between minus 1 and 1, if I is 1 over x, get flipped, just like the 1 over y did. So there's your range. Okay, they start repeat. After one complete revolution, period is 2 pi. So here's my summary. Domain, set of all x's, such that x does not equal an odd multiple of pi over 2. Range, minus infinity to minus 1, and 1 to infinity. Period, 2 pi. Vertical asymptotes, x equals an odd multiple of pi over 2. Again, the basic period is going to be between 0, x equals 0, and 0, x equals 2 pi. So the graph. Again, we're going to sketch in the cosine of x lightly and then flip it over to get the y equals secant. So we're going to draw the vertical asymptotes at s equals an odd multiple of pi over 2 and reciprocate the graph of y equals cosine of x. Translate the basic period by 2 pi in order to fill up the graph. So here's the cosine of x. Okay, the vertical asymptotes will be at x equals pi over 2, 3 pi over 2, 5 pi over 2, negative pi over 2, and so on. So they're my vertical asymptotes. Okay, so one chunk is going to be right in here, another chunk down in here. But again, the basic period looks weird. The basic period looks weird. If you fill it up, there it is. So those dark red ones is the cosecant. Now, if you put some count, that looks like the secant. Yeah, if you didn't know where the y-axis were, you couldn't tell. Okay, if you didn't know where the vertical asymptotes were, you couldn't tell. Just like sine and cosine look alike, secant, cosecant look alike. Now, the question is, the last two, tangent, cotangent, will they look alike? Kind of. So y equals cosecant of x, y equals secant of x out of phase by pi over 2, just like their reciprocal functions. So if you wonder on stock code and say, something's out of phase, you know what they're talking about. So the graph of the cotangent function. So domain, range, period, and asymptotes. Again, I remember the cotangent was y over x. Aha, I got issues with x again. On the unit circle, I'm going to have x being 0 at 0, 1, 0, negative 1, the north and south poles, odd multiples of pi over 2. So x equals odd multiples of pi over 2. Those are going to be left out of the domain. Those are going to be the vertical asymptotes. So we have a vertical asymptote of x equals an odd multiple of pi over 2. Our graph is in pieces. So the domain is set of all x's such that x is not equal to an odd multiple of pi over 2. Now, just like the tangent wasn't as the tangent is y over x, not the cotangent is x over y. The reciprocal of a real number is another real number. So the range is just like the tangent. It's all real numbers. The period is pi because tangent and cotangent use both x and y, so it cuts the circle in half. The graph of y equals cotangent of x. So I'm going to sketch the asymptotes and the basic period in the open interval from 0 to pi. Notice you can never use x equals 0, you can never use x equals pi. So there are my vertical asymptotes. There's the basic period. You can see it does kind of look like the tangent function, except it seems to be twisting in the other direction. Remember, the tangent would have done something like that. Now to fill up the rest of it, again, notice you have x-intercepts at x equals an odd multiple of pi over 2. You have vertical asymptotes at x equals a multiple of pi. You don't have a y-intercept. And the period is pi. And again, the tangent and cotangent seem to twist, so they're not considered to be out of phase. Again, kind of notice the same with the trig function. Either all 6 do it, or else 2 and 4. 4 of the 6 trig functions are out of phase, the other 2 are not. So the summary of properties of the circular functions. So we're going to summarize what you as a student should know about the graphs and properties of circular functions. So I've got my little table here, my 6 trig functions, sine, cosine, tangent, cotangent, secant, cosecant, domain, range, period, asymptotes, and is it continuous? In other words, does it occur in one piece or not? Okay, for the sine, domain, minus infinity to infinity. Range, minus 1 to 1. Period, 2 pi. Asymptotes, doesn't have any. Continuous? Yes. The cosine, Domain minus infinity to infinity. Range minus 1 to 1. Period 2 pi. Asymptotes? No. Continuous? Yes. Okay, the tangent. The domain. Remember, the tangent was y over x. So on the unit circle, x is 0 at odd multiples of pi over 2. So x is not equal to odd multiple of pi over 2. Range, all real numbers, minus infinity to infinity. Period, pi. Asymptote, x equals an odd multiple of pi over 2. Continuous? Nope. The cotangent. Remember, the cotangent was x over y. Y was 0 at the multiples of pi. So the domain is x does not equal a multiple of pi. Range, all real numbers, minus infinity to infinity, period, pi. Okay, the asymptotes, x equals a multiple of pi. Notice the asymptotes and domain are kind of related. Continuous? Nope. Okay, the secant. Remember, the secant was the reciprocal of the cosine. So its domain is minus infinity to minus 1, union 1 to infinity. Okay, or x does not equal an odd multiple of pi over 2. The range, oh, excuse me, that's the range, minus infinity to minus 1, union 1 to infinity. Period, 2 pi. Asymptotes, x equals an odd multiple of pi over 2. Continuous? Nope. The cosecant, that's reciprocal of sine. So the domain is going to be x does not equal a multiple of pi. Range, the same as the secant. The period, 2 pi. Asymptotes, x equals a multiple of pi. Continuous? Nope. Here's your big summary. And of course, most of them we forget. And it's one of those, if you think your way through what the trig functions are on the unit circle, you should be able to recover this. Okay? It is important that you know the zeros of the trig function as well. Remember, the zeros of a function correspond to the x values of the x-intercepts. Not all the trig functions have zeros. The split is still 4 and 2. So, zeros and y-intercept. That's and y-intercept. I should have made my space bigger because it looks like I spelled and. So, zeros and y-intercepts of the trig functions. For the sine. Okay, remember, the sine is equal to 0 at x equals a multiple of pi. The y-intercept, 0, 0. Cosine, its zeros are x equals an odd multiple of pi over 2. The y-intercept, 0, 1. The tangent, the zeros, x equals a multiple of pi. The y-intercept, 0, 0. Notice it's kind of like the sine, kind of weird. The cotangent, the zeros, x equals an odd multiple of pi over 2. Y-intercept doesn't have one. The secant, the zeros, there aren't any. Remember, it spits out numbers that are bigger than 1 or less or equal to minus 1. So zeros, none. Okay. Remember, the secant is the reciprocal of the cosine, so it should have the same y-intercept, 0, 1. The cosecant, it's like the secant. It has no zeros. The cosecant is the reciprocal of the sine, so its y-intercept, but remember, it can't get down to 0, 0. So, it does not exist. And again, remember, zeros are the x-coordinates of the x-intercepts. Some examples. Answer the following. What is the period of the cotangent function? Now remember, cotangent on the unit circle uses both x and y. That cuts the period from 2 pi down to pi. True or false? It is possible for sine of t equal to negative 1.5 for some value of t. False. Remember, the sine and the cosine spit out values between minus 1 and 1. So false, and here's your reason. Number 3. What are the zeros of the cosine function? Okay, remember, the cosine function did something like this. Okay? So that's x equals an odd multiple of pi over 2. The end of section 6.5. Now again, you can use your graphing calculator to graph anything at all. Just for the trig functions, be sure you're in radian mode.